Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 9 from the June 2023 International A-Level Pure Mathematics P2 paper. And this question here is about trigonometry. Part A is about trig identities. And it says, show that 3 cosine theta, then in brackets tan theta times sine theta plus 3 is equal to 11 minus 5 cosine theta, can be rewritten in this form as 3 cosine squared theta minus 14 cosine theta plus 8 equals 0. So this equation can be rewritten in this form. Okay, so there's a few things that we should think about before we start. Now in P2 there's two fundamental identities that we need to know, and one of them is that the tangent of any angle is the same as the sine of that same angle divided by the cosine of that same angle. Okay, that's one identity. And the other one is when you take the sine of an angle and you square it, so the sine squared theta, that's the sine of an angle, and you square it, and you add to that the cosine of that same angle, and you square that, will always give you 1. So sine squared theta plus cosine squared theta equals 1. Okay, and then sine squared theta actually means sine theta squared. That's what it actually means. And this is cosine theta squared equals 1. So the sine of an angle squared plus the cosine of the same angle squared will always give you 1. So these two identities are very important for us to know, to memorize. And those are the main two identities that we'll be using in any P2 questions. And all identities in further, like P3 and P4, that we're going to be using will be based upon these two main identities. All right, so now, keeping that in mind, we've got to think about a strategy. We have to end up with everything in terms of cosine thetas. Okay, so what I'm going to do is, if you look at this side seems to be okay. I can just leave that as it is. But this side, what I can do is I can first of all I can rewrite tan theta as sine theta over cosine theta, as we know from this. So what I'm going to do is I'm going to write this as 3 cosine theta, and then in brackets, now tan theta I'll write as sine theta over cosine theta, and that's times sine theta, so times sine theta, plus 3, close the bracket, equals 11 minus 5 cosine theta. So now when I expand this, or before I actually expand it, I can write this as 3 cosine theta times, and this is going to be sine squared theta over cosine theta plus 3, okay, equals 11 minus 5 cosine theta. Now I can expand this bracket here. So when I multiply 3 cosine theta by sine squared theta over cosine theta, the cosine thetas will cancel. So I'll be left with 3 sine squared theta. And when I multiply 3 cosine theta by 3, I'm going to get plus 9 cosine theta. And that's equals 11 minus 5 cosine theta. Now what I can see here is I have everything in terms of cosines. 9 cosine theta and minus 5 cosine theta. If I actually bring them together, I'll end up with 14 cosine theta if I put them this way, and minus 14 if I put them that side. So that looks like it's quite promising so far. But here I have sine squared theta. I don't want any sine squared theta. So what do? Well, I use this identity here. I know that from this identity, I can rewrite sine squared theta as 1 minus cosine squared theta. Just rearranging this identity. So I can replace the sine squared theta and write it in terms of cosine squared theta, which is what I want, because we want to have only cosines in our equation. And that will help us hopefully get to this. So sine squared theta, I'll replace it with 1 minus cosine squared theta plus 9 cosine theta equals 11 minus 5 cosine theta. Okay. One of the big mistakes people make is this only true for sine squared theta and cosine squared theta. You cannot say that sine theta plus cosine theta equals 1. That's not true. Okay, sine theta plus cosine theta does not equal 1. Only when they're squared and you add them together, you equal 1. All right, so that's a very big misconception. Like somebody might think, let's replace this sine theta with 1 minus cosine theta. You can't do that. All right, so it has to be squared. So in this case, I can replace this with 1 minus cosine squared theta, and then we can continue. So that's like one misconception that people do get muddled up with. So now we're going to expand this. So you have 3 minus 3 cosine squared theta plus 9 cosine theta equals 11 minus 5 cosine theta. Now what we have to end up with is this, where the cosine squared theta is a positive term. So what I'll do is I'll just keep this side as 0, and I'm going to add 3 cosine squared theta to both sides, in which case you'll end up with 3 cosine squared theta on this side. And I'm going to take away 9 cosine theta from both sides, so I'll end up with minus 14 cosine theta. And then I'm going to subtract 3 from both sides, so I'll end up with plus 8. Okay, and that's exactly what we had to show. Yeah, so we can just rewrite it. 3 cosine squared theta minus 14 cosine theta plus 8 equals 0. So there we have the answer to part A. Just like using these two identities basically to rewrite this in this form. Okay, there's part A. Now for part B, it says hence, meaning using this result that we got this becoming that, solve for theta or for x by, between 0 and 360 this equation. Now the difference between these two equations here is simply that instead of theta, okay, instead of theta here, we have 2x. Okay, so that's the only difference between them. Everything else is the same. 3 cosine of the angle times tan of the angle times sine of the angle plus 3 equals 11 minus 5 cosine of the angle. So the angle has now, the theta has become 2x, that's all. So I can rewrite this as the same as that, except instead of theta, I can rewrite it as 2x. Okay, so I have 3 cosine squared of 2x minus 14 cosine of 2x plus 8 equals 0. Now, in order to make life a bit kind of easier, we could think of this as a disguised quadratic, and to make things more familiar, we can say, for example, let, say, u equals cosine of 2x, which means that u squared will be cosine of 2x all squared, which is cosine squared of 2x. So what I can do is I can replace the cosine squared of 2x with u squared. So this will become 3u squared minus, and you have 14u plus 8 equals 0. And I can solve this for u, and then I can find out what cosine of 2x is for them. All right, so what I'm going to do now is I'm going to factorize this. I'll see, can I factorize it? So I like to factorize if things are able to be factorized using this kind of window method, as we call it. It's just basically splitting the middle term in a visual kind of way. So what I do is I write the term here, 3u squared in the top left, and the bottom right I write the number 8 there, the number term, and I multiply these together. That gives me a product of positive 24u squared. And I have to find a sum that gives me the same. I have to find the two numbers which give me the product of the same thing, 24u squared, but a sum has to be minus 14. The sum has to be minus 14u. So you think of all the ways of getting 24, and I know they both must have the same sign because the product is positive. They both must be negative signs. Negative times negative gives you positive. When you add them together, you get some negative. It looks like it's 12 times 2, isn't it? 12 times 2 is 24, and 12 and 2 gives me 14. So I have minus 12u here and minus 2u here. Okay, then what I can do is I can take out the common factor from these two terms here, 3u squared and minus 2u. The common factor is u. Then I can say u times this gives me 3u squared, that's 3u. U times minus 2 gives me minus 2u. 3 times this gives me minus 12u, that's a minus 4. So I end up with 3u minus 2 times u minus 4 equals 0. Now many students ask, is it okay for us to use this method? Of course it's okay to use this method. You can split the middle term in the traditional way by, rewriting this as 3u squared minus 12u minus 2u plus 8, and then factorize by grouping. That's fine. It's exactly the same thing actually, but this is just like a visual way of doing that same thing. So whichever way you prefer, that's fine. Now we can say, say that either 3u minus 2 equals 0, in which case u is equal to 2/3, or u minus 4 is equal to 0, in which case u is equal to 4. So now we can replace our u with what it actually really is, cosine 2x. So we got cosine 2x equals 2/3, and we have cosine of 2x equals 4. Now, for cosine of 2x equals 4, we should understand that this will give us no solution. Okay, because we know that the cosine curve, okay, will have a maximum value of 1 and a minimum value of -1 if there's no vertical transformations, and there's no vertical transformations here. This only has a horizontal transformation. So this is going to give you a maximum of 1 and a minimum of -1. So it can never equal 4. If we try to find, if we try to use a calculator and say inverse cosine of 4, we will see degree mode inverse cosine of 4. We will see that it will give us math error because there's no way it reaches that. So we know that there's no solution to this, but cosine 2x equals 2/3, that will have a solution. So what we do is we find the first solution using the calculator. That's called the principal solution. So we'll have inverse cosine of 2/3, and that gives us 48.189. Okay, I'll write it like that, 48.189 continues on. Okay, that's, I'm right, leaving it to, more decimal places than needed. Of course, we have to round it to 1 decimal place, even if it didn't tell us. That's what we do for angles. All right, so that's called the principal solution. Okay, so the angle 2x equals 48.189. Now, that's basically an answer somewhere over here. Okay, that's where 48.189 is. There's another angle, okay, which is all the way over here, which shares the same cosine ratio of this. Okay, but before we actually go into that, we have to be very careful here, because our limits are from 0 to 360 for x. From 0 to 360 for x. Now we're solving for 2x right now. So we got to change the limits, and whatever we do to the x to make it 2x, we do to these numbers. 0 times 2 is still 0, but 360 times 2 is 720. So we've got to catch all the angles between 0 and 720. So this is one of those angles. It's 360 minus 48.189. So that's one of the angles. Okay, that's the other main angle. So this is the first main angle, okay, which you get by the calculator, and the other angle is 360 minus that angle. Okay, so it's going to, if this is 360 here, this is 48.9. This is also 48.189. Okay, this distance, but it's that much less than 360. So for the cosine curve, you find the main angle and 360 minus that main angle to give you the two main solutions. Okay, so we do 360 minus that answer, and that gives us 311.810. 311.810. So those are the two main solutions, okay, in our steps so far. But now we got to go all the way up to 720. And the sine curve will have another two solutions up to 720. If you think about it, 720 will be over here. There's going to be another two solutions, one over there and one over there. Okay, so we can basically think about this solution is 360 more than that solution, because it repeats every 360. So if I add 360 to this, that will give me another solution. And if I add 360 to this, it will give me the other solution over here. And you'll see that both of them are going to be within our range of 720. So if we go back to this angle and add 360 to it, that's going to give us 671.810, 671.810. And if I add 360 to this, that's going to give us 408.189. We're just adding 48 and 360, that gives you 408.189. So we have four angles. We have 2x equals, you have 48.189. Then you have 311.810. Then you have 408.189. And then you have 671.810. Those are the four angles for 2x. Now what we have to do is we have to solve for x. Okay, and then of course we have to find out what x is. That's how we solve the equation. So we want to now take all of these angles and divide them by 2. Okay, so let's start with this one. Divide this one by 2. Okay, that gives us 335.905. Okay, 335.905. And then we have to go to this angle over here. Okay, so let me just go back to the original. All right, so we did this 360 plus this would give us the answer. That's going to be 408. Divide that by 2. That gives us 204.095. 204.095. And then we have this 311. So if we get this answer by doing 360 minus the original answer, which is this, divide this by 2, and that gives us 155.905. 155.905. And then we have our original answer. Okay, the original answer here, which is this. We divide that by 2, and that gives us 24.095. 24.095. So now we're going to just, in the end, write all our answers to one decimal place. You have 24.1 degrees, 155.9 degrees, 204.1 degrees, and 335.9 degrees. Those are the 4 angles which are within our range, okay, from 0 to 360. And those are the solutions to this equation. Okay, so that kind of sums up this question about trig equations. So we were dealing with the cosine curve. Just a little summary for you in case you weren't aware or you have some problems. If we were dealing with the sine curve, okay, we want to find the values for the sine curve, all right, and you're solving equations involving sine of an angle. The first angle is always found by using a calculator. The second thing is you do, for sine, you do 180 minus the calculator answer. Okay, that will give you the 2 main solutions. And then every other solution will be plus or minus 360, okay, from these angles. So if you take these answers and you add 360 to them and subtract 360 from them, okay, you'll get the other solutions. You keep adding 360s and taking away 360s. Why? Because the sine curve repeats itself every 360 degrees. So that's the sine curve. All right. Now, if we're dealing with the cosine curve, okay, if we're dealing with the cosine curve, all right, the calculator answer, that's the first thing you do. Then you do 360 minus the calculator answer, because the symmetry of the cosine curve is such that 360 minus the answer you get from your calculator will give you the other solution which shares the same angle. And then after that, again, you just add 360s to both of these main 2 solutions and subtract 360s from them until you're out of the range that you need. And then you have the tan curve, which is a bit simpler actually. Okay, so number 3, the tan curve. So for tan x, the first thing you do is you do the calculator answer, and then that's it. Everything else is plus or minus 180. Okay, so the tan curve just has like a main solution, and that solution repeats itself every 180 degrees. So you add 180s to your answers, take away 180s from that answer until you're outside of the range. So that's like some basic rules, and they're based upon the symmetry of those curves. So the sine curve between 0 and 360 looks like this. So if you have an angle over here that the calculator gave you, there's going to be another angle which is 180 minus that, which is here, which will be the other main solution. And then because the sine curve, the symmetry of the sine curve, they repeat every 360 degrees. So the angle will repeat over there, the angle will repeat over there, and so on, even backwards. For the cosine curve, it looks slightly different. Between 0 and 360, it looks like this. So the calculator will give you, for example, this answer, and the answer over here is 360 minus the answer because of this symmetry. This is the same as that. That's 360 degrees. So whatever this angle is here that your calculator gave you first, this angle will be 360 minus that, and then it repeats every 360 degrees. And for the tan curve looks a lot different. You have these shapes that repeat, like this is your asymptotes. It doesn't touch them actually, but goes like this. So this angle here is your main solution, for example, that you get, and this angle is just 180 more than that, and then it repeats. There's another one angle over there which is 180 more than that, and there's an angle back here which is also 180 less than that. So it's just that same angle repeats every 180 degrees. So that's some of the reasoning behind this. You can also use the cast diagrams, as many people like to do. I personally think this is way less confusing. It's easier to just think about it in terms of the symmetries and get the answer straight away. But you can use the cast diagram, as they call them. I like to call it the ASTC diagram, right? And you just use the symmetry. You find the principal or the associated acute angle. Okay, so for example, for the sine, it's going to be positive in these two. All right, so you're going to have an angle here and you're going to have another angle over there. Okay, but for cosine, it's positive in these two. So you're going to do this angle and you're going to have this angle all the way around there, which is 360 minus that angle basically. So, that's another method as well. As I said, I personally prefer this method here, just understanding from the symmetry of the curves how to deal with it. Okay, so that's just a little summary for you of how to deal with solving trig equations, and you'll find some more examples in the playlist if you want to have a look where I've answered more in-depth questions about them. All right, so that concludes this video on question number 9 from the Pure Mathematics P2 June 23 exam. Any questions that you want to see from the rest of the paper can be found in the playlist that will appear in this region over here for the paper, and there'll be a playlist over here for trig identities and equations from P2. You can subscribe to my channel by clicking on this link, and the link over here will take you to a video which tells you how to use my channel to find those things that you're looking for. Thank you for watching, and see you soon.